So I've already written out example 2, and I'm going to talk you through it. This one is an interesting one. So one way I can do this is I can find the Maclaurin series for e to the x and find my radius of convergence and show that it's true for x element of reals. But I can also use this idea from my Maclaurin series that if the limit of the absolute value of the error term is equal to 0, then the Maclaurin series is the same as the function. So if I think about my Maclaurin series for e to the x, that's going to be the sum of x to the n over n factorial. My error term for the nth term is going to be the, oops, I should have said that this was the n plus 1th derivative, evaluated at c, x to the n plus 1 over n plus 1 factorial. Well, my nth derivative or n plus 1th derivative of e to the x is e to the x. So I get that my Rn is going to be e to the c x to the n plus 1 over n plus 1 factorial. So I want to know, does the absolute value of that limit equal 0? Well, if I look at this, e to the c is going to be positive. I can bring it in front. So now I want to look at this. Well, looking at this takes a bit of manipulation. And so there's always going to be some value k that's going to be between the absolute value of x and n. So we're always going to be able to find some value k that's bigger than absolute value of x and smaller than n. That means that if I look at absolute value of x to the power of n plus 1 minus k, so I'm going to have n plus 1 minus k terms that are all going to be less than k, k plus 1, times k plus 2, times k plus 3, down to n. So this ends up creating the same number of terms here. So if I want to find number of terms, take last value minus first value and add 1, which is what I have here. And this is true because k is bigger than x, so multiplying k and then multiplying by numbers bigger than k is going to be bigger than repeated multiplications of x. All right, so now if I come back to here, take my entire term, dividing by the n plus 1 factorial, well, I know it's positive, so I know it's greater than 0. And from what I've said here, I also know that it's going to be less than my x to the k power, and then my remaining terms are going to be these terms, and this is what's making it less than, because with just this I'm still equal to. So here's my less than bit. If you think about expanding your n plus 1 factorial, you have 1 times 2, da 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 da, k minus 1, k, k plus 1, etc. So I can cancel this out and cancel it out here. That's going to leave behind absolute value of x to the k over k minus 1 factorial, so that's going to be these terms. This is going to be some sort of constant over n plus 1. So looking at this limit, I can say that this limit is less than, so this limit is less than limit as n goes to infinity of absolute value of x to the k over k minus 1 factorial, so that's a constant, 1 over n plus 1. So here's the only place that I have an n. As n goes to infinity, this becomes 0. That means by squeeze theorem, I'm between 0 and 0. This limit must become 0. So since my error term, the limit of the absolute value of my error term equals 0, therefore, my Maclaurin approximation is valid for all x element of reals.